In this tutorial, I'll introduce heated floors and show you how to model them in Designbuilder. During the tutorial, I'll discuss aspects of heated floors that you should understand before modeling them. I'll introduce the internal source, which enables you to provide heating or cooling via internal constructions such as floors and ceilings. I'll load the hot water heated floor template. I'll then edit the loop and system components so that they're appropriate for the heated floor system in this model. And finally, I'll run a quick simulation and discuss the results. Heated floors in Designbuilder are low-temperature radiant systems comprising of hot water pipes embedded within the floor construction. The general operating principle is a system with a large heat-emitting surface area and low surface temperature. The maximum acceptable floor temperature for floor heating in occupied areas is around 29 degrees C. Floor heating systems typically use low flow temperatures of around 40 to 50 degrees C, compared with around 80 degrees C for traditional low temperature hot water heating systems using radiators and convectors. You can see from this indicative boiler operation graph that the lower water return temperatures enable condensing boilers to operate in condensing mode more often, resulting in higher seasonal efficiencies. When using more insulating floor surfaces such as wood, you may need to consider increasing the flow temperature to overcome the additional resistance to heat transfer. Underfloor heating can be used with most floor finishes, but is best with concrete and stone tiles, i.e. exposed thermal mass with good conductivity and low surface resistance. The maximum output from a floor heating system is much lower than many other types of heating system and may not be sufficient to meet the higher heating loads in older, poorly insulated and leaky buildings. Floor heating requires an insulation layer below the embedded tubes to prevent heat leakage downwards. Floor heating systems generally have a slow response time, as the heating pipes provide indirect heating via the mass of the floor screed. It takes longer for the screed to heat up and cool down than emitters such as radiators and convectors. This can result in zone temperatures deviating from set point temperatures if the heating or cooling loads in the zone change quickly, through solar gain or natural ventilation cooling, for example. Designbuilder can realistically model floor heating systems. However, as highlighted earlier, there are real-life issues with this type of system, and these will be reflected in the model results. There's some really useful guidance on troubleshooting problems with heated floors in the help file. One further general comment. When using heating sources such as condensing boilers and heat pumps that operate best with lower flow temperatures, you may need to consider providing separate domestic hot water systems, as these require higher flow temperatures. Domestic hot water will be discussed in another tutorial. There are a number of settings to consider in the Model Data tabs, so I'll do that at building level before setting up the heated floor. In the HVAC tab, I'll load the most relevant template, which in this case is the underfloor heating system nap vent. And I'll leave the outside air definition method set to minimum fresh air per person. I'll leave most of the activity tab set points at their default values, but will reduce the nap vent cooling set point to 0 degrees C, so that natural ventilation is provided according to the minimum fresh air setting and occupancy schedule. Going to the construction tab, I'll create a new ground floor construction and then show you how to specify the details of the embedded pipes in the floor construction. I'll start by copying this best practice ground floor construction, and then edit that to meet my needs. I'll call it Tutorial Ground Floor. This is an externally insulated construction, so I'll delete the existing outermost layer, place the cursor in layer 2 and insert a new insulation layer above the concrete slab. I'll specify an insulation layer of PIR unfaced at 200mm thickness. I'll load the cement screed finish as it has a higher conductivity. I'll change the screed thickness to 40mm and the floor covering to a more conductive tiled surface. And I'll assume a thickness of 10mm. I'll leave the remaining floor construction details at default. Using the Image tab, I'll confirm that the layer details are correct. Before looking at this internal source tab, which is only visible with detailed HVAC set in model options, I'll just note that the hot water pipes would be located between the insulation layer and the floor screed, i.e. between layers 2 and 3. An internal source must be defined for all zones containing heated floors, as this is where you define the parameters for the heating pipes inserted between two layers of a ground floor or internal floor ceiling construction. If you try to model a heated floor in a zone without an internal source, the simulation will generate an error. I'll set the internal source after layer 2. You can also use this set source position below innermost layer tool for appropriate constructions. This dimensions option enables you to specify the complexity of the calculation method used in the simulation. The 1D or one-dimensional calculation option is suitable if the heating or cooling plant performance is not too sensitive to return water temperatures. The 2D option is more complex and should be used with plants such as heat pumps and condensing boilers that are sensitive to return water temperatures. I'll use the 2D option for this system as I want to model the benefit from lower boiler return temperatures. As I'll be using a condensing boiler, which operates most efficiently at lower flow temperatures, I'll reduce the tube spacing to 200mm. This will provide a greater heat output from the floor and is one of the settings you should consider if your initial results indicate that you're not meeting the set point quickly enough. Having created the tutorial ground floor construction, I'll load it at building level. The internal floor construction will be different to the ground floor. So for the purposes of this tutorial, I'll copy the new ground floor and create a very simple construction called tutorial internal floor. I'll save it in the internal floors folder and reduce the insulation thickness to 50 millimeters and I'll load that as my new internal floor construction at building level. You could also use subsurfaces to apply patches of floor heating within a single zone. This may be required to accurately model a heated floor where the pipes don't cover the whole floor surface for practical reasons, or in a low energy building where the heating load is so low you'd only need part of the floor surface to meet the demand. I'll now go to the HVAC system level. I'll load the heated floor hot water template, assign that to all zones, and retain the default settings. Most of the hot water loop and boiler inputs have been discussed in previous tutorials, so I'll only amend the settings required to make this system operate appropriately. I must, of course, ensure that my zone sizing data is correct and will retain the defaults for this tutorial. Going to the loop level edit dialog, I'll change it to a variable flow system with a design loop exit temperature of 60 degrees C, so that Energy Plus sizes the boiler using the same maximum operating flow temperature that I'll specify later in the hot water loop setpoint manager. I'll leave the availability schedule set to on so that the system is controlled according to the heating setpoint schedule in the Model Data HVAC tab, enabling me to provide setback heating outside occupied hours. Going to the boiler edit dialog, I'll specify an efficiency of 90%. The minimum and maximum part load ratio options enable you to determine the operating part load ratio above and below set criteria. There is more information on this in the help file, but the default settings mean that these ratios will not be used to modify part load operation, which will simply follow the boiler efficiency curve. The optimum part load ratio is the part load ratio at which the boiler performs at its maximum efficiency, but is only used when the plant loop's load distribution scheme is set to optimal. A typical value will be 1 for traditional plant, but for condensing gas boilers the optimum part load ratio is much lower at about 0.3. As discussed earlier, these types of system operate most efficiently with the lowest possible flow and return temperatures. In the set point manager, we can use the outdoor air reset control type, which is called weather compensation in the UK, to reduce the flow temperature below its design maximum as the outdoor air temperature rises and the heating load reduces. Here I'll use an outdoor reset set point of 60 degrees C for an outdoor air temperature of -3 degrees C and below, and 30 degrees C for an outdoor air temperature of 21 degrees C and above. The flow temperature will vary in a linear way between the low and high temperature set points. Domestic hot water would need to be provided via a separate system, as the DHW flow temperature needs to be much higher than efficient space heating flow temperatures outside the peak heating season. Navigating now to one of the zone heated floors, I'll review the edit dialog. The constant and variable flow options here dictate the required data inputs in this dialog, and I'll review each in turn, starting with constant flow. This diagram shows how constant flow heated floors modelled in Designbuilder are simulated in Energy Plus. The hot water flows from the heating plant to the various secondary heated floor circuits. These contain 3-port mixing valves, which allows the amount of primary and recirculation flow to be varied according to the zone heating demand. A pump is included in the secondary circuits, and the temperature sensor controlling the flow temperature from the 3-port valve is located after the local pump to ensure that the correct heated floor inlet temperature is used, accounting for any temperature variation across the pump. Going back to the constant flow edit dialog inputs, you'll note that there are no auto size options. So the tube, flow and pressure parameters are required from design data. The tube and flow details affect heat transfer as they determine whether the flow is laminar or turbulent. The tube length is the length of tube serving the heated floor in that particular zone. The rated flow is the maximum flow required to meet design conditions. The pump details dictate the pump energy consumption and the temperature rise of the fluid across the pump in the heated floor circuit. The pump flow rate schedule can be used to modify the maximum flow rate at specific times. Note that the operational availability is scheduled separately below. The control schedules here enable linear operation of the mixing valve between high and low water temperatures to control mixing within high and low zone temperatures, i.e. dead band above and below the zone set point. This is explained with the aid of a diagram in the constant flow heated floor help section, showing that the flow temperature decreases as the outside air temperature increases. Once the minimum flow temperature at maximum outside temperature set point is reached, then the system switches off. This diagram shows how variable flow heated floors modelled in Designbuilder are simulated in Energy Plus. The hot water flows from the heating plant to various secondary heated floor circuits. These contain a two-port throttling valve which allows the amount of primary flow to be varied according to the zone heating demand. As the zone heating demand reduces, the two-port valve closes to limit or stop the hot water flow to the heated floor. The balance of the flow simply bypasses the secondary circuits. As the two-port valve closes, the pressure in the primary loop increases. This results in the controller reducing the pump speed to maintain a constant pressure. As power consumption is proportional to the cube of pump speed, this can result in significant energy savings under part load conditions. Note that the pump is on the return side in Designbuilder models. Going back to the edit dialog, I'll select the variable flow option. Fewer inputs are required for the variable flow system due to constant pressure operation. Unlike the constant flow heated floor, the tube length and flow rate options are auto-sizable. Remember to either use auto-sizing or manual inputs at component level. Don't try to mix and match. This throttling range input is again described diagrammatically in the help file. The heated floor control valve throttles the flow from 0 at no load to full when the zone temperature is below the lower limit. Using the default 2°C throttling range as an example, the upper and lower limits will be 1°C either side of the zone set point. I'll leave the heated floor set to variable flow with defaults as I've no design data available, and apply this to all zones using the Target tab. Before running a simulation, there's one more thing I need to do to give me visibility of the floor surface temperatures in the simulation results. In the Model Data Options tab, under the Simulation Output Options, Graphable Output Options, I'm going to tick the Store Surface Output option and select the inside surface temperature. I'll now simulate a winter design week at 10 time steps per hour. And I'll use operative temperature control, as this is a radiant system which will provide better control but will also increase plant sizes due to the impact on radiant temperatures of the lag in fabric thermal response. There's a useful discussion on using operative temperature control in the help file, which I would advise you to read if you haven't done so previously. I'll now review some selected zone simulation results. Using operative control results in a longer warm-up time than we've seen previously using air temperature control due to the lag in rise of fabric temperatures suppressing the mean radiant temperatures. Here you can see that the set point is not approached until late in the morning. This is why energy consumption can be higher using operative control. Zone temperatures are generally less stable due to the response lag from the underfloor heating system. Note the spike in temperature after Wednesday and Thursday lunchtimes, with high solar gain and reduced nat vent from lower occupancy. This further highlights the slow response time of some underfloor heating systems, as it takes time to release the thermal energy stored in the mass of the floor slab. There is no heat gain from the heating system shown in the heat balance graph, as the heat emitter is actually the floor surface. Because I saved the surface temperature data, I can navigate to the floor surfaces and see the inside surface temperature, which shows the heat input to the zone. These show a peak floor temperature of around 28 degrees C, so there's still scope to increase the heat input to the floors by measures such as reducing the tube spacing. In this tutorial, I've shown you how to set up a heated floor system in Designbuilder, including the requirement to set the internal source in the floor slab. I explained how underfloor heating systems work and how the constant and variable flow systems are simulated at Energy Plus. We then saw some results which reinforced some of the issues with underfloor heating, such as the problem of slow system response where you have rapidly changing heat gains in a zone.